Hi everyone, this is Yifei from HKUST. It's very honored to be here in virtual UAI to share you our work, Complete Dictionary Learning via NLP norm maximization. This is a jointly work with Yifei, Shen, Professor Zhang, Professor Letaief, and Professor Vincent. First of all, I'd like to introduce the background or the motivation of this work. We know that natural signals are complicated, so people have been seeking for centuries to find a good data representation. We start from 1800s Fourier transformation to 1900s wavelet transformation. Until nowadays, we're using deep learning, which learns the data representation in a cascaded way. So these are all efforts that trying to answer how to find good data representation. In this work, we are not only interested in how, but also want to answer why. However, simultaneously answer these two questions is difficult. So here I quote Robert Gallagher, who said it is human nature to prefer simplicity. So we're going to start from a very simple problem and trying to fully understand it, and then to get some insight, and finally we can generalize it into complicated problems. So what is a simple data representation? We think that sparse data representation is simple, because we can use only a few number of non-zero elements to represent a high-dimensional data. So finding the most sparse representation turns out to be a problem called dictionary learning, which aims to learn the unknown transformation D and the unknown sparse representation X from a given data Y. The problem can be directly formulated into this one. Here, L0 norm is using to counting the non-zero elements in X. So here we have got the simple problem. Can we answer the question how and why? No, because this problem is not simple at all. Because we are now facing high-dimensional data, and this L0 norm here and the bilinear constraint here will make this problem highly convex and NP-hard. In addition, for an efficient learning algorithm, we would like to learn from as few as possible samples. So the target of this work turns to design an efficient algorithm to learn the optimal dictionary with tractable sample complexity. So before we start, we would like to have some preliminaries. In this work, we are focusing on complete dictionary learning. Here, complete means that the dictionary D is assumed to be invertible. And by the results in this paper, we know that any complete dictionary learning problem can be converted into an orthogonal dictionary learning problem. So in this work, we assume that the data is generated by an orthogonal dictionary D node and sparse coefficient X node. And under this assumption, we can multiple D at both sides of this equality to obtain this formulation. However, in this formulation, there's still an L0 norm, which is highly complicated to deal with. So people have transformed it into its approximation by using L1 norm. And in this work, the authors have proved that this problem can be solved to achieve the optimal solution. However, L1 norm is non-smooth, so it will dramatically slow down the convergence of the corresponding algorithm, and also it will make the algorithm very sensitive to the parameters such as the learning rate. Therefore, here comes the problem. Can we use other norm to relax this L0 norm? Meanwhile, to avoid the issues caused by L1 norm. It turns out that if we constrain the sparse representation X node on an unit L2 norm, minimizing any LP norm with P between 0 and 2, or maximizing any LP norm with P larger than 2 are equivalent, in the sense that they have the same optimum. So here is a figure that shows this conclusion. Therefore, in this work, we're gonna choose maximizing LP norm with P larger than 2, because in this case, the object function is smooth, which will accelerate the convergence algorithm. And more importantly, as can be shown in this figure, each time when we're trying to maximize this object function, we can transform it into maximize its tight lower bound, which is a very simple linear function. And it achieves its optimal at the boundary. So we do not need step size at this case. And we then got our formulation, which is very simple by just transforming the minimized L1 norm into maximize LP norm. This transformation is simple, but it will improve a lot. After we got the formulation, we can find an efficient parameter-free algorithm to solve it. Just as I mentioned before, we can solve it by successively maximize its tight lower bound. So the resulted algorithm is very simple. At each iteration, you just need to calculate the gradient and then do the projection. And there's no parameters to be returned. The next question is, can this maximizing LP norm formulation provably recover the true dictionary? We proved in the paper that under some statistic model, when X naught is following the Bernoulli-Gaussian distribution, which is a widely used sparse distribution, maximizing any LP norm with p larger than 2 can recover the dictionary when the sample size is large enough. Specifically, the sample complexity grows polynomially in terms of the dictionary size m, and grows exponentially in terms of the choice of p. And this figure shows that the sample complexity grows exponentially in terms of p. And we also did some experiments. This experiment shows that smaller p will bring us a more accurate result, and a smaller p will also has a faster implementation because it has less computation in each iteration. So in this way, we thought that L3 is the best choice because 3 is the smallest integer, which is larger than 2, right? And we also test the robustness compared to other baselines. We find that surprisingly, maximizing L3 norm can recover the dictionary very accurately, even with Gaussian noise. We also showed the theoretical proof in the paper. Therefore, here I want to conclude our work that LP norm maximization enables efficient and robust solution for complete dictionary learning. And there is a very simple parameter-free algorithm that can be used to solve this LP norm maximization, which is tractable and optimal achievable. We also proved the convergence result in the paper. Finally, among all the choices of P, we thought that L3 is the best. That's all. Thank you.